So we have another lecture, so you must be tired, but the good news are this is the last before the least, so you're almost done. And so what I'd like to drive you into is a process that is very important in cosmic evolution, and it's called cosmic reionization. I will divide my lecture essentially in two parts, two sub-lectures. Lecture 1, which is properly on the physics of cosmic reionization, and the second one will have to do with the most promising technique by which we will be studying cosmic reionization, which is 21 centimeter line intensity mapping. So let me start by giving you a very broad overview on the topic. I know that you have already seen most of these things, so it's just a recap, but to put things in context. So this is the timeline of the events in the cosmic evolution, and we have already seen yesterday from the CMB another diagnostic that the recombination occurred around redshift 1000. So this is where the CMB radiation is originating and is coming towards us from the last surface, or the surface of the last scattering. From 1000, redshift 1000, so 300,000 years after the Big Bang, and redshift around 40, which correspond to about 100 million years after the Big Bang, essentially we can say nothing happened. So the universe was dark, the light from the CMB shifted from the visible into the infrared regime. Therefore the universe was dark, and not by chance, this epoch is called the Dark Ages. So it was very quiet and very quiet phase during the evolution. It's only around redshift 40 that, due to the gravitational instability, collapse of the gas into nonlinear structures, the first stars form. Okay, these are often called population tree stars because historically there is a ranking of the stars according to their age: Pop 1, Pop 2, Pop 3. So Pop 3 are the ancient one, and they also happen to be metal-free. So they do not contain heavy elements as the present-day stars. So these are this is the first light in the universe. Okay. So the impact of the formation of the first stars was tremendous on the gas, which was essentially containing, the intergalactic gas was essentially containing almost the totality of the baryons in the universe. So the universe was in gaseous phase, and so because of the radiation field, the energy, the radiative energy the stars were emitting, the universe started to be ionized, so the gas of the intergalactic medium, the IgM, started to be gradually ionized, and this is the process that we are studying today. This is called reionization. And then the rest of the story is more or less clear. So then the galaxies grow larger and larger due to merging and accretion, and the cluster are assembled later on. So this is, as I said, this is my first sub-lecture, so cosmic reionization. Before I do anything else, I'd just like to point you to some reviews that you can read if you're interested in deepening your understanding of this cosmic reionization. So there are things that are historical, which are nevertheless useful if you're starting to approach this material, and there is more recent material. I leave the slides later, so you don't need to copy them now. Okay, so let's start simple. So if you have a source, there is emitting ionizing photons. I recall you that in order to ionize a nitrogen atom, you need photons with an energy of 1 Rydberg, that is 13.6 electron volts. Helium can also be ionized, but requires higher energy photon. First ionization potential of helium is 24 eV, and the second is 54. So let's talk about hydrogen here, but keep in mind that there is also helium-2 reionization. The processes are similar, but for sake of clarity, I will concentrate today only on hydrogen reionization. So good. So if you have a source, there's emitting ionizing photons at a rate which is given by this term. So this is the number of ionizing photons larger than 13.6 eV that are produced per second. So the ionizing photons emitted by the source are balanced by recombination occurring into the gas. So electrons join protons to form neutral hydrogen atom. This is called recombination. And so there is a coefficient, the recombination coefficient. I don't want to go to the details of that, but so these two rates must be determine essentially the size of the volume, the physical volume of this ionized bubble. Let's in a simple case in which everything, the density is uniform, you have a point source producing an H region. Okay. So the physical volume of this bubble is Vp, and also you have to account for the fact that while you're doing that, the universe is expanding. That's why the Hubble constant is there. So this is in physical coordinates. We can also transform that equation and go into moving coordinates. And we also introduce what is called the so-called clamping factor. Clamping factor is nothing else than the variance of the density. So you can allow for the fact that the density is not perfectly smooth and uniform, but has clamps or inhomogeneities in this that are in a very rough and simple manner embedded into a single value of the clamping factor C. In comoving coordinates, the previous equation reads like that, where now we have the comoving total hydrogen density, NH0, and the rest is the same. So this is a simple ODE that can be really integrated to obtain the volume of the ionized region as a function of time. So it's a simple integral over the ionization rate times the factor that contains the clamping factor and the scale factor A. Okay? So very simple solution. So this is how a source produces a bubble, and how big is this bubble is a function of time. That's step number one. Of course, in the real universe, we don't have singles, so we don't have one source. We have a combination of several sources. So we can extend a little bit the simple approach to step number two, in which we treat the volume of the ionized bubble in a more statistical sense. How do we do that? Well, we do that by introducing what is called the porosity factor Q. So Q is nothing else than the ratio of the volume that we have just computed, the volume of the H region or H2 bubble, over some representative volume of the universe V that you're interested in studying. Okay, so how do we do that? So we essentially we recast the previous equation by substituting solving for Q instead of V, and then we have also to introduce two other things. So first of all, there is a ratio of the number of ionizing photons per baryon that you put in a given structure. This is a very important quantity in realization, so pay attention to this, and I'd like to stop for a second and comment. So the key issue here is that if you take the baryons and you put them into a halo, for each baryon that I put there, how many ionizing photons do I get out? This is a very important number. So this, how do we compute that? Well, the first step is just to factorize this term into two quantities that we know well, or we think we know relatively well. The first is the fraction of matter that is collapsed into nonlinear structure, so it's a collapsed fraction. And this comes from essentially the theory of gravitational instability, or that is incarnated into the Press-Checker formalism, if you like, or any numerical simulation that can tell you what fraction of the matter in the universe is contained in nonlinear structures. The other term is has to do with the baryons. And this is called the efficiency of the ionization, which in turn is a product of three numbers that we know so and so. And this is, we're starting to see what are the difficulties of predicting reionization exactly. So these three numbers are the number n gamma is the number of photons that you produce per baryon that you put in stars. Okay? So that depends on the initial mass function of stars. For example, today in our galaxy, the stars are formed according to Salpeter IMF, power law, that is called the Salpeter IMF with slope minus 2.35. And so for each, if you say that stars form according to this IMF, then for each baryon that you put into this type of stars, then you get 4,000, roughly 4,000 photons. Okay? For each baryon that you put in stars, you get 4,000 ionizing photons out. Okay, so this is relatively well known. This is the most solid among these three numbers. The second factor, F star, is if you put these baryons into a nonlinear structure, how many of these baryons end up in stars? So this is the efficiency of star formation, and this is called F star. Typically, as a rule of thumb, people take something which is between 1 and 10%, but of course it depends on a lot of processes like feedback and complex non-linear dynamic, linear hydrodynamics of baryons into halos. So take a 10%, but it's a little bit uncertain. And finally, the most uncertain of all is now that you have put the baryons into stars, the stars have produced ionizing photons. What fraction of these ionizing photons are able to escape into the intergalactic medium, which is the system that you want to ionize, and this is called the escape fraction. And this is essentially totally unknown. It's very hard to determine what is this number. We will see later how we can get at least some ideas on that. Nevertheless, so the procedure is the same as before, but now in terms of Q of T, and so that gives you an idea of what fraction of the cosmic volume as a function of time is filled with ionized gas, as opposed to neutral gas. That is the beginning of the story. So the yellow word reionization model is the following. This comes from the solution of the equation that I just showed you. So this is Q. This porosity factor as a function of redshift. Okay, so you see that you start low because you don't have a star initially, but as the stars continue to form and structure evolves, then this porosity increases and reaches 1, and that depends on the details, of course, of all these three numbers. This is just an example. I'm not claiming that this have any bearing with reality, but you see that essentially you can already see that for a number of different models, you get reionization that from redshift 6 or so, or up to 15, depending on the value of the parameter that you choose, and also on the clamping factor that they're assuming. Good. So this is just to first of all, we see that reionization, first of all, is a monotonic process. So in the past, people have also tried to produce models that have some wiggles and minima and so on and so forth, but these are now very much excluded. So the first thing that we learn is that the simple model already tells us something important. So the reionization proceeds in a monotonic way, and going from low ionization to full ionization, which will be achieved at some point that we'll see later. Good. Now, this is the end of the sweet part. Now the hard part comes, because if you really want to do a proper transfer rather than this ionized bubbles simplification in which everything is spherical and some blah blah blah, we need to deal with the very difficult issue of cosmological radiative transfer. So we want to do radiative transfer in an expanding universe. And this, as you can imagine, is not simple, simply because what we would like to obtain the specific intensity of the radiation field at a given frequency at every location in the universe. It's a function of 7 different variables, okay? Because you have time, 3 spatial variables, the angle, and the frequency. So the equation of cosmological radiative transfer is this, and so there are essentially 4 terms. So it says that the way in which the specific intensity of the radiation field in the universe evolves with time at any position depends on different physical processes that are outlined here. So the first of all, the first term corresponds to the redshifting of photons. So you have to take care of the fact that while photons are emitted, the universe is expanding, and so these photons are progressively redshifted as they move away from the source. The density also changes as the photon propagate. they change because the universe is expanding. So again, the H, the Hubble constant appears there. The photons can be absorbed, so this is an absorption term, or also emitted, because the gas can also emit the radiation itself. So this equation is very complex, as I said. There is a formal solution which is of little use because it's an implicit form which cannot be actually inverted. And so but it's just nice to see that we can introduce the optical depth, which is nothing else than the integration of the absorption coefficient K along the line of sight. So there is redshift. This frequency at any position depends also on the expansion. This is standard redshifting of photons. Okay. So the most drastic approximation that you can do, you say, okay, I assume that my photons, the mean free path of my photons is much shorter than the Hubble radius, which corresponds to say that the absorption coefficient is much larger than h over c. And in that case, you can have a very approximate form for the J, for the specific intensity as a function of time. That depends on the emissivity of the sources as a function of time, times essentially the mean free path, or the inverse of the absorption coefficient. This at least can give you more or less a first order estimate of the intensity of the field, but of course it's a very rough approximation. So how do we make progress on this? Well, we had to turn to numerical solutions, and all of them have pros and cons. I'm not going to deliver here a lecture on the computational methods for radiative transfer because it would be too much. But just to give you an idea and to provide you some references, there are several numerical solution techniques that have been proposed. Essentially, they divide in 2 or perhaps 3 categories. There are techniques that essentially do some form of ray tracing. So they have a source and you try to follow you cast rays in all directions, and you solve the 1D radiation transfer equation along that ray. These are all the family of ray tracing characteristics. And then there are other methods like the flux element tensor, the flux limited diffusion, in which essentially you treat the photons as a fluid. So the fluid, you insert a new equation, hydrodynamical equation for the photon fluid. This is an approximation that has many troubles because it's very diffusive and so on and so forth. Then there are other type of methods, and also there are also statistical methods with use Monte Carlo sampling of the photon propagation. So, but there is a very huge field of numerical simulation to include radiative transfer simulation, and depending on, it's very complex. Also, computation is extremely expensive. So, if you do any radiation hydrodynamic simulation, typically is about 5 to 10 times slower than the pure hydrodynamical simulation. So that is a problem, of course. Nevertheless, so how do we know which is the best solution or best technique to solve our problem? Well, there has been the approach has been to do benchmarking of codes versus codes. So we compare different codes with all these different techniques, and we see how they perform on problems for which we have some analytical solutions, simple problems. And the first one, of course, is our beloved single bubble models, or the Strongren spheres are called. So these are 3 among the models the codes actually that participated to an extensive benchmark testing of these codes, those cosmological radiative transfer codes are doing. So these are more or less the 3 families that I was saying before. So these are the ray tracing, this is statistical, Monte Carlo, and this is the photon fluid approach, so the flux limited density. So you see that the Strongren sphere should be a simple problem to solve in 3D. It's not exactly so. Some codes are not doing very well. Then you can go to even other type of comparisons, like suppose you have a dense clump which is illuminated by some radiation that is coming from the left, and so there is a shadow behind the dense clump. And again, you see how things are different codes. What I'm showing here is the temperature. Well, no, actually, this is ionized fraction. So you see black is neutral. So you see this part is ionized, and again, there is some ionization also on the back due to the scatter radiation. And this is also the most difficult test to do. This is what we would actually like to use. All these codes is the cosmological field, in which you see that the blue is where the gas is totally ionized, pink is neutral, and so there's a transition. You see a lot of structure can get very complex once you have many sources that are interacting with each other. So more or less, within 10%, we think that the technical part of the reionization is, I don't say solved, but it's under control. So we know exactly more how big the errors are and in which situation we have to be careful. But so the technical part of reionization, in some sense, is under control. Now the rest of the physics.
Yeah, it's about 10% from the top to the middle, the bottom panels on the right.
This diffusion, these are the flux limited codes that in fact have larger uncertainty. But if we know in which conditions these things happen, so we can. What I should say is that we can estimate the error depending on the conditions of the gas. Okay, so we know which conditions some codes fail bad. Well, not so badly. Fail things. So they are less correct. But technically speaking, this is the best that we can do, so it will take time before we can improve on top of this. But after all, I would say that these are not the major problems in understanding reionization. We have other problems that I explain in a second. So if this is the case, then let's see what these methods applied to cosmological simulation with radiative transfer of cosmic reionization can tell us or can teach us. So this is the first, I'm giving you a glimpse of the reionization process right away, and then we come back to analyze a number of details. So what I'm going to show you in the next few slides is results from simulation in which you will see 4 panels. This is the top here, top left is the neutral hydrogen fraction, so the neutral part. This is the specific intensity of the UV background in units of 10 to the minus 21 ergs per second per square centimeter per hertz. This is the gas superdensity, so you see the relation between the reionization pattern and the gas superdensity, and this is the gas temperature, because remember that to each ionization there is also a photoheating of the gas associated to it, because the electron that is stripped from the atom delivers its kinetic energy to the gas, and therefore this corresponds to an heating. At the center you have also, you can follow the scale factor, which is the inverse of 1 plus z. Good, so initially, as you said, we are here redshift 12 in this simulation. We see that in the simulation box there is a huge bubble here that corresponds essentially to this star-forming region. Okay, so this is the red here, is where the density is higher, with the first stars are forming here. And so there is a stellar clump that is producing this ionization bubble. And the first thing you can note is that the size, the shape is more or less spherical, even though you would think that the stars are sitting here. No, they are sitting at the bottom, but the bubble expands in this direction because you see a point here. So it's easier for the bubble to go this way than on the other side, where there's a lot of density. So then we continue, and more stars are formed. For example, there's another star forming event here, another here, and so the structure starts to become much more entangled. So our simple spherical approximation clearly breaks down. Note that in the temperature pattern, you see that the regions that are ionized tend to achieve a typical temperature, which is 10 to the 4, which is essentially set by the equilibrium between photoionization, heating, and cooling by essentially neutral hydrogen, so Lyman alpha cooling. I'll come back later to this point. And you see that the mean flux, the mean intensity of the field, J, is also steadily rising. So we continue with this pattern. The gas becomes, even in the most oldest H2 regions, the gas starts to become more and more ionized. You see the blue part, which correspond to 1 neutral hydrogen per 10 to the 4 hydrogen atoms. So there's very little neutral hydrogen left here. And so the process continues. And now you see something interesting. You see that there is a steepening of the radiation field. This marks the time at which the mean free photon path becomes comparable to the Hubble radius. That implies that at any point in the universe start to see not only the nearby source, but all the sources that are located at cosmological distances. And so there is a boost in the radiation field that you see grows very much. Actually, probably the best definition of the reionization redshift is exactly where you have this steepening of the flux. So this is exactly where the time at which the mean free path of ionizing photons becomes comparable to the Hubble radius. To me, is the most physically meaningful definition of the reionization redshift, which in this case should be around 6.5 or something. And then note that now the topology of the H2 of the reionization has changed. Instead of having small ionized regions embedded into a sea of neutral gas, now after the steepening, the opposite is true. You see that there are instead pockets or islands of neutral hydrogen that are embedded in an otherwise ionized intergalactic medium. So most is blue, but there are these pink remnants here and there, which shrink because now they are illuminated from the outside from the general UV background. So this is the time at which we have a UV background. That means that the spatial intensity of the radiation field is essentially uniform. So that's why we can talk about of a UV background, while in the first phases there are large fluctuations. Inside the bubble we have a very large field, outside was essentially zero. Okay? Now everything is smooth and flat and uniform. And so finally, we get to the very early stages of reionization where you see that everything is ionized, but you can still recognize the remnant of the filaments. So the filaments are overdense structures with overdensity of about 10 to 30 times the mean are still there, and they are slightly less ionized than, for example, the voids, where the neutral hydrogen is essentially gone, or it's less than 10 to the minus 5, and this is the very final stage. And so at this point we say the reionization is completed. So this is the process that we can follow in very much detail. This is really, it's amazing that we can get to this detailed description of reionization from the point of view of the global evolution and the topology, which in 3D looks like that. So you have redshift 20, you have these small bubbles, redshift 16, the bubble merge, and then over and over exactly. This is a 3D rendering of the same thing we've just seen. So now, this is one simulation that we have performed. We can do many, and they probably would all produce the same pattern of evolution. So the things that I explained generally, so the various physical processes that are occurring and the topology is roughly the same. But is that correct? I mean, we want to know more. We want to learn exactly how reionization occurs. So in order to have better constraints on the unknowns that are the ones that I mentioned before, the physical unknowns, we need to resort to combine these numerical experiments with real experiments, with data. And so for a long time, and perhaps even now, the best diagnostic, the best experimental diagnostic of reionization has been the so-called Garth-Peterson effect. So this is has been a very influential work that Gunn and Peterson produced in 1965. So about more than 50 years ago, but it's still used as the top diagnostic in order to study cosmic reionization. So how does it work? Well, historically, Gunn and Peterson noted that in 1965, there was a quasar that was just discovered. It was 3C9, a quasar located at redshift 2. Okay? And so Gunn and Peterson look at the spectrum of this quasar and note that there was a very prominent Lyman alpha line. Now, this Lyman alpha line not only was there, but was also very symmetric. Okay? Now, for reasons that I'll explain in a second, if you think that the gas between us and the quasar is totally neutral, the Lyman alpha photons emitted by the quasar would be scattered away from the line of sight, particularly those on the blue side of the line. I'll explain that in a second. So you should see essentially something which is very asymmetric. So you see the red part of the line, but you should not see the blue part of the line because of the scattering. But that was not true. The line was very symmetric. So Gunn and Peterson said they concluded that most of the gas in the intergalactic medium must be ionized. So that was the first, to my knowledge at least, the first time that the idea that the intergalactic medium is not neutral, the gas in between galaxies is not neutral, but it's ionized, was proposed. And they were absolutely right. So let's see what is the argument. So the scatter, if you take a Lyman alpha photon that is emitted by a source, or any photon, as we will see in a second, at wavelength shorter than the Lyman alpha line, should be scattered by the intergalactic medium as it travels towards us. And so the probability for the scattering, taken in the historical paper by Gunn and Peterson, the probability P, is nothing else than the product of the density of gas that it encounters along the path, the cross-section for the Lyman alpha, which is given by this expression in terms of the fundamental constants, and the line profile G, and also the length of the path that the photon is traveling. So this essentially corresponds to an optical depth, so it's a product of density times sigma times length, and so it's an optical depth. And so in the modern days, we can rewrite this formula in something that for us is perhaps more transparent. And so we define what is called the Gunn-Peterson optical depth as a function of redshift. Okay? So this is the formula that we use to interpret the data, and that depends on the parameters like the omega matter, omega barium, because they enter into the geometry essentially, redshift to the 3/2, so it's a steep dependence on redshift, and also the fraction of neutral gas with respect to the total hydrogen gas. Okay? So now you see that this factor is very large, it's 4 times 10 to the 5, which implies that by redshift 6, for example, neutral fraction of 10 to the minus 4 is already tau equal 1, so it's complete Gunn-Peterson absorption. So it takes only a little bit of neutral hydrogen to produce a substantial optical depth. So even those filaments that we were seeing as the remnant of our simulation of the transfer have an neutral hydrogen fraction which is 10 to the minus 4, 10 to the minus 5, and that produces substantial obscuration of the light that is coming to us from it.
So in that case, the full line will disappear, not only the blue side of it.
Well, it depends. If tau is very larger than 1, so you start to go to 3, 4, and 5, yes, then there is something that is called the damping wing, and so the absorption line becomes as a dent profile, and that eats also part of the red width of the line. So the more if you're in a neutral medium, essentially, also the red parts get eaten away. So you see exactly as we see in the next slide, by the way. So this is what's happening schematically, right? So if you start from a high redshift where the gas is neutral, and then you go down to a low redshift where it's all ionized, as we have seen in the simulation that I showed you before. Essentially, there are three regimes of Gauss-Peterson absorption. So if your source is located, like in the original Gauss-Peterson paper, redshift 2, okay, where the gas is totally ionized, so the only thing you see is that, that the photons that are at wavelength shorter than the Lyman alpha are progressively redshifted until they get in resonance with the Lyman alpha line, and there they are absorbed. And so that produces, essentially maps all the high density or neutral regions that are along the line of sight in a structure in the spectrum that is called the Lyman alpha forest. So you see that there are discrete absorbers every time that the photon gets redshifted at the right position where there is some neutral hydrogen. And when I say some, keep in mind that I'm talking about 10 to the minus 4, 10 to the minus 5, so very little H1. So this is the Lyman alpha forest. This is what you see in the spectra of quasars that are located in the post-reionization epoch. Okay? Now, if you are in an intermediate situation in which we are still, in which we have bubbles and discrete bubbles immersed into in a roughly neutral background, then we have what is called the patchy absorption. So some patches that are totally neutral absorb the photons for a very long stretch. And so you see these dark gaps that are appearing in the spectra, so intermixed with the forest. So there are regions that are transparent, but then there are also regions like, for example, this one in which you have complete absorption. And then if you put the source into the neutral gas, so prior to reionization, then you have a complete Gauss-Peterson trough. That is what we observe, for example, in quasars at high redshift. Now, this is a schematic representation, but we do see exactly this thing in all quasars. So we can line up all the quasars that we know as a function of redshift, and you see that as you go from low redshift, these are all high redshift anyway. So this is 5.6, and this is 6.4. So you see that, for example, in the 5.7 quasar, there are regions where there is transmissivity. This is the Lyman alpha. So to the shortwards of the Lyman alpha, there are regions where transmissivity occurs. But as you go up, the spectrum becomes essentially blank. There is total absorption. Still, there are some redshift 6.4. There are some regions where you have some small transmission. So there could be some ionized stretches in the gas. So if you put together all we know on the Gauss-Peterson, then these are the quasars from redshift 3 to redshift essentially 7, the most distant that we have. So you see that the rise of the optical depth as a function of redshift is more or less gradual. The dashed line that you see underneath the points here is the simple analytical formula that we were obtaining before. So the points are okay, so they follow up this line. But we see something apparently happening at redshift about 6, where it seems that a rise is a very steep rise with a power larger than 10. It's ramping up into the Gauss-Peterson optical depth. So this could be, and we think that this is a signature of reionization. Of course, the Gauss-Peterson, the problem we have here is that the most distant quasar that we have available, and there's only one, is a redshift 7.1. Well, maybe now there is this discovery of a new 7.5 quasar that is going to be announced soon, but still the numbers are very small to allow us to do this experiment with detail and to decrease the error. So the uncertainty remains, so the technique is there, but we miss quasars or high redshift sources. You could do the same experiment also, for example, with gamma ray bursts, but gamma ray bursts are much more abundant than the quasars, and also they have spectra that are less clean to do this type of analysis than the quasar. So Gauss-Peterson is the top diagnostic for reionization so far. The second in the second part of my lecture today, we will instead discuss another new technique that we plan to use is 21 centimeter intensity mapping, but I'll come to that later. So the second point that we need to make here is that while the Gunn-Peterson is telling us, is giving us some constraints on the behavior of the optical depth, this is something that simulation should be able to reproduce. Now, there are, in addition to, that's why I was saying before that the technical part is not the problem. Solving the radiative transfer equation is not the main problem of reionization. The main problem is the physics, and particularly the physics of the sources, because we don't know, as we are speaking, we don't know what are the actual sources that produce reionization. We only know more or less that reionization happened, but we have hints, but not yet any solid answer. For example, the sources that have been considered as possible sources for the ionizing photons that we need are definitely, the most natural one would be stars, okay? So we have two stars coming to flavor, as I said before. So we have population two stars, normal stars, and by that I mean stars with the saltpeter IMF, more or less normal saltpeter IMF, or massive stars, or Patchy stars, which could be massive or not massive. So we know, we have never observed a Patchy star, so we don't know, but for sure they were there. The universe started with metal-free. And so also in what proportion it's these stars, how there's been a transition from POP3 to POP2 stars is not clear. It's not something that is irrelevant because for example, if you check the difference between population 2 stars, they produce, as I said before, 4,000 photons per baryon into such population. POP3 stars with the same saltpeter IMF would produce 30,000. And population 3 stars, if they are all massive, they will produce 100,000 of ionizing photons if you put one barrier into those stars. So understanding the proportion and what type of stars that produce ionization is key, and you can get ionization history that are very different. So alternatively, you can use quasars. We know that quasars are there. Although there has been recently revival of the role of quasar in reionization due to the newly measured luminosity function at high redshift, still we think that quasars are too rare. So they are there, they are luminous, but they are too rare, and they come too late. So we know that their number density peaks around redshift 3, so probably they come too late. But they could be key sources, for example, for the helium-2 ionization, also because they have a lot of hard photons in their spectrum. Supernova explosions are essentially ruled out because they would produce, it could produce ionized gas by mechanical injection with shocks, but it would also produce a lot of hot gas, and so the limits of the Compton-Wine parameter that we were discussing yesterday are already limiting this type of sources in a very severe manner. More exotic things involve dark matter annihilation or decays, and several models have been attempted to include this type of sources in the models. Essentially, all of them came to the conclusion that at best you can produce an optical depth of electrons of less than 1%. So essentially these are ruled out, but they could be important for the heating of not for the ionization, but they produce heating of the IgM, and that is something that could be potentially very important for 21 centimeter studies. So to the temperature of the IgM at high redshift could give us hints on the possible decay or presence of decaying or annihilating dark matter particles. Finally, in the exotic parts, we also have mini quasars, I don't want to go into many details. So these are essentially the progenitor of the supermassive quasar that we see. They also produce X-rays, and so the X-ray background limits their contribution again. And finally, structure formation can also produce some brainstorm radiation as the halos are collapsing, which could produce some light. But so we are left with stars and perhaps quasars, but stars are also have a lot of uncertainty within this precise interpretation of the sources. So now I'm going through the CMB very fast because you've seen everything yesterday. So just to mention that in addition to the Gam-Peterson, CMB is also affected by reionization in essentially 3 ways. So there's a damping of the primary anisotropies on all scales, but this is a very an effect which is extremely difficult to measure. Small scale secondary anisotropies that are caused by patchy reionization can be a nice way to study also the CMB, but the most successful so far technique has been to look for the large scale polarization signal. And the thing is interesting because while the Gam-Peterson measures the optical depth of neutral material, the optical depth to electron scattering that we can measure from the CMB give us an integrated measure. So it's a complementary measure because now here we are measuring the ionized part of the intergalactic medium, but we only have one single number to describe the entire distribution of electrons. So this is the formal expression for the electron scattering, which is the integral over again over the mean-free path, weighted by the Thomson optical section, and this is again the formula for the tau e as a function of redshift. So this is very simple. Again, you see that the dependence on 3/2 is exactly like for the Gam-Peterson because the formula is essentially the same. Okay. So very quickly, so these are the polarization maps, and this is the impact that the reionization may have on the EE and TE spectra. So you see this bump here, this extra power that appears at low multiples compared to the spectrum that you would get without the reionization. So the best constraint that we have now, it's at least last year it was like that. So it's an optical depth 5.8%, which is relatively low, and you can translate. We always have to be careful when we transform optical depth into a reionization redshift, because typically what is assumed is that you have a step function evolution of the ionized fraction. So you say that everything is neutral to that redshift and then everything is ionized. So it's fine. We can do this transformation, because it's interesting to transform optical depth into redshift. But keep in mind that actually the reionization history is much more gradual than what assumed when you do this translation. Now, so what are the other all experimental constraints that we can hope to have in order to be able to make progress? So we have already seen the first. We have already seen the first two, which is the Gam-Peterson and the electron scattering from the CMB. But there are additional ones, additional experimental data that we can use to constrain reionization. And certainly, there are other lines that we can use, for example, the Lyman data, Gam-Peterson opacity. We can study independently how the UV background intensity rises with time. We can look at the temperature evolution of the intergalactic medium, the metallicity, because the photons that are emitted by stars are often associated by metal production by the same star, because they are massive stars that are dominating both the photon production and also the heavy element production. And then general statistical quantities like the cosmic star formation history, counts of high-redshift galaxies and the near-infrared background. These are all statistical quantities that you can put together. So ideally, reionization models should be constrained by all these data sets together, and one can also attempt to do something like this by having general models based either on simulations or semi-analytical models to put together all these constraints, a little bit like we do with the CMB. So we have all this data, we have a model, so we can optimize the parameters of the model via MCFC techniques. And so this is what you get as an example of how we can constrain ionization using all these data sets that we have available. So this is our beloved quantity, this effective ionizing photon per pairing to stars. And so the black curve is the mean value that we get from the model, and the dashed line is the fiducial that is based on educated guess of the free parameters that you would put into the models based on physical considerations. So we can fit at the same time, for example, the emissivity, the photoionization rate, the evolution of these pockets of absorbing gas that we call Lyman limit system. There are still remnants of the reionization. We can look at the evolution, we can constrain the evolution of the porosity factor, and the evolution, perhaps the most important quantity, the evolution of the neutral hydrogen fraction. So the red points are data from Peterson and other data sets from GRBs, DLAs, and so on and so forth. So basically you see that there is still a big uncertainty. So if you take the mean, so it's clear that the data suggests that the ionization, the neutral hydrogen fraction decreases with redshift, so this is redshift 5 to 15, but the uncertainty are still high. So at this stage, we have not yet a precise model of reionization, and which implies that we cannot be sure of what are the sources and how reionization is tied to galaxy evolution. Right? So this is still a lot of work to be done in that area. Now, if you take a model like this, which is trying to put together all the available data, so this is consistent with all the available data we have, even though the data are not sufficient to pinpoint exactly the reionization model. What can we learn? Well, there are many things that we can learn as a return from this model. And I just thought to comment one of those. So if you ask to this model, once you have fit all the available data, so okay, what are then the sources, what are the galaxies that produce most ionizing photons if the reionization model is the one that I just showed? Well, this figure answers that question. So this is the fraction of the total ionizing photon that we produce through cosmic time, produced by halos with mass larger than the number that's within the horizontal axis. For example, at redshift 7, you may say that essentially more than 80% of the ionizing power comes from halos that have masses less than 10 to the 9 solar masses. Okay? So one important thing, which I think at this point every person that is working in the field agrees, is that the reionization has been predominantly produced by dwarf galaxies or small galaxies, small systems, not the big ones like the one that we are observing right now, redshift 7 or 8. So these are very faint galaxies that produce a very distributed ionization patterns, and they produce most of the photons that reionization uses in order to ionize the intergalactic medium. So this is one of the interesting results from this type of studies, and there are other questions that on which we can make progress by combining models, simulations, and experimental data. This is very important. The interrelation is very important. Otherwise, we would not be able to do much. Now, this is the present situation, but this all said today may change dramatically in the next 5 years, because we are in an epoch in which we are almost ready to take a new step, instead of looking at integrated or redshift dependent properties of reionization, we will be able to map the ionization field exactly as we have seen in the simulation before, with a technique that I'm going to explain in the second part of my lecture. And this has to do with the H1 21 centimeter line intensity mapping. Okay, so what is that? This is the future in the reionization field, and we are all working very hard on that now. What is the key point? We have seen that the Gunn-Peterson uses the Lyman alpha line as a powerful probe of the reionization, but the Gunn-Peterson effect essentially blanks out the high redshift unit exactly the time that we would like to study, because the Gunn-Peterson, as you enter a little bit into the true reionization epoch, the Gunn-Peterson blanks away all the spectra of different sources, so it cannot be used efficiently. The CMB, as I said before, provides only integrated measurements of the optical depth, so there's no sensitivity to a specific redshift, while we would like to do something which is more keen to a tomography of the universe. We want to slice it, slice by slice, and see how the maps of how reionization proceeds. So the idea, and the next step to overcome this problem, is to use the particular line, which corresponds to the spin flip hyperfine transition of neutral hydrogen. And so this is due to the electron-proton-magnetic interaction involving the spins of the electron and of the proton. So how does that work? Well, you have a proton in a hydrogen atom, neutral hydrogen atom. You have spin, for example, suppose that the spin of the proton is aligned with the spin of the electron. That corresponds to the excited state of the hyperfine transition. It happens that from time to time, due to the process that we'll study, there is a spin flip. So the electron flips the spin, and the small energy difference associated with this transition corresponds to a line frequency, which is exactly the 21, what is called the 21 centimeter line, or frequency of 1420 megahertz. Okay, so this is a line emitted by a neutral hydrogen atom. Good. So what do we do with that? Well, we would like to study how this line is transmitted from the gas to us. And again, there's our below radiation transfer equation comes in again, because the intensity of this line as a function of frequency, the specific line intensity as it propagates along the path L, depends on is written in the standard way, in which we have the line profile times the energy of the line, and then we see here that there are different processes that involve the Einstein coefficient, so the spontaneous emission, absorption, and stimulated emission. So all these processes change the line intensity as the line propagates, as the photons propagate towards us. So N1 and N0 are the number of hydrogen atoms that are sitting in the upper level with the parallel spins. With respect to the ground state, with anti-parallel spins. Okay, so it's the density of these atoms in these two states. How do we know that? Well, this is the standard Boltzmann equation that is telling us that the ratio between the excited and the ground state level is equal to their degeneracy, which is 3 and 1, times the exponential that depends on the temperature. And actually, this is important because this is the equation that defines, actually, you can take it as a definition of what is called the spin temperature. Okay? Spin temperature Ts is this quantity that essentially is a way to express the relative population of the levels. and T star is the, which is equal to 68 millikelvin, is the energy gap between the two states. Now, in general, because this energy difference is so small, the spin temperature that we will see soon is typically coupled to the temperature of the radiation field, which, as we'll see, is the CMB. So it's usually much larger than that, and so because T star is much less than Ts, that essentially implies that N1 over N0 is equal to G1 over G0, which is equal to 3, okay? So roughly it's a fixed number. So this also implies from the previous equation that the N1 term equal to 3 times N0 implies that the stimulated emission cannot be neglected during the transfer. Okay, so now in radio astronomy, of course, I forgot to mention, but of course we are talking here of radio astronomy because we are in the 21 centimeter regime, which is in the radio, and even more because this line is red-shifted. So we are talking about typical frequency ranges that are 1420 megahertz divided by 1 plus z. So we are talking about redshift 9. That would correspond to 140 megahertz. So it's really low frequency radio experiments, okay? And there are several experiments that are going after this, and probably the most important one that you will hear in the next few years is the SKA, the square kilometer array, which is essentially the perfect interferometer to do this type of work. I have no time to go into the description of the experiment today, but just to let you know that maybe this is something that it's truly taking off and coming soon. Now, suppose that well, in radio astronomy, it's because we are working at low frequencies. It's instead of using the specific intensity I, radio frequency, we work in the Rayleigh-Jeans approximation, and in which the black body distribution function becomes approximated by this expression. So the I would be just 2 kb nu square over c square. So we can define what is in radio astronomy is called the brightness temperature, which is a simpler way to describe the intensity of a given light, so the specific intensity, okay? So with some maths that I'll leave you as an exercise at home, you can recast the original radiative transfer equation in terms, instead of the intensity, you can use brightness and introduce also the optical depth, okay? So let's see, this is again the radiative transfer equation written in terms of temperatures rather than intensity, nothing special. Also tau appears, the optical depth of the line that I'll discuss in a second. What I'd like to discuss here is to be clear about what these terms are. So T prime B is the brightness temperature of the cloud in its framework, in the rest frame, okay? TB instead is TB prime over 1 plus Z, that is the observed brightness temperature, the thing that we receive on Earth. T prime R is the brightness of the background radiation field along the line of sight. And this is important. So what are we doing here? It's just what we would like ideally to measure is the emission from a neutral gas cloud, okay, located in the reionization epoch. But of course we have to keep in mind that behind this cloud there is the CMB, or any radiation background that we have, okay? So what we are actually measuring is two things. It's the sum of the light emitted by the cloud, but also the light that is coming through the cloud by the CMB. And you can, this equation explains very well this concept. Suppose that your cloud is totally transparent, okay? So tau will be equal to 0. So if you put tau equals 0 here, this term goes away, and what you see is only TR, so the background radiation. If instead tau is very large, so the cloud is optically thick, then the background gets totally absorbed, and you don't see it, and you only see the emission from the cloud itself. Okay, this is what the physics that this radiative transfer equation explains. So very simple. Now, the key point here is what is tau. So how do we know if this cloud is transparent or is optically thick? Okay, so then we have to define the optical depth, which in principle formally is very simple. So again, is the integral over the size of ds of the alpha nu, the absorption coefficient, which as we have seen before, depends on the Einstein coefficient. So again, this is absorption minus the stimulated emission, which you can think as negative absorption. Okay, so you subtract whatever the cloud itself emits rather than absorb. And so this is your alpha, and you put it there. And the derivation is again similar to the Gauss-Peterson opacity. So I'm not redoing it. So you integrate over this equation over the cosmological path, and at the end of the day, you get the optical depth from the excited to the ground level, which is equal to this quantity. Now, this tau, as you see, is very small, so it's of the order of 10 to the minus 3, differently from the Gauss-Peterson. So remember that the coefficient before was of the order of 10 to the 5. Here it's 10 to the minus 3, okay? Then, again, the three halves dependence, as usual. Neutral hydrogen fraction, spin temperature, and then this cosmological term, with the only exception here that you have to keep in mind that there could be also, because it's a line radiation transfer, we also need to integrate over the line profile, and so we have to be sure that there are no velocity gradients. We could produce Doppler effects of the line. So, but these are details. So the important thing is that we have an expression for tau, then what do we do with that? As I said, what we observe is the density contrast between the cloud and the background radiation, so TB minus TR, and the background, as I said, is the CMB. So the 21 centimeter experiment observed emission or absorption of a given patch of neutral hydrogen in the universe against the CMB. Now, we have seen that the tau is small, 10 to the minus 3 roughly, as an order of magnitude. So we are safe to make this approximation that tau nu is much less than 1, which simplifies our transfer equation into something very manageable, which says that the brightness temperature at a given frequency that I observe is equal to the difference between the spin temperature of the cloud and the microwave temperature at that redshift. And this is multiplied by tau. And again, if you want to say, so how intense is the radiation that I can measure from that patch of neutral gas? Well, this is the answer. It's, on average, it's 9 millikelvin times all these factors. So you multiply by redshift, so of course it's convenient to go to observe this radiation at the highest redshift that you can, because it increases with redshift to the 1/2 in the most overdense parts, because the gas is denser, it emits more, and of course you have this factor, cosmological factor, and then the important one, which is here. So this is essentially containing almost all the physics. The rest is cosmology, mostly, okay? But this is the physics of the 21 centimeter radiation. So let's analyze this term a little bit in more detail. As you see, first of all, it's a term that depends on the ratio between the CMB temperature and the spin temperature, exactly for the reason that I was telling you before. So you need to have some contrast between these two radiations, otherwise you cannot disentangle them. So suppose that Ts is larger than T gamma, then this term is less than 1, and so 1 minus that is positive. That means that TB is positive, and so the emission with the radiation, I will see a signal in emission. Okay? If instead Ts is less than T gamma, so the spin temperature is below the CMB, then this term becomes negative, and I get a negative TB, which corresponds to absorption. So I see an absorption against the CMB. Now, note that while in emission, this ratio, this term cannot become larger than 1. In absorption, the signal can become arbitrarily large. So in principle, it would be more convenient to look for the signal in absorption than in emission, but you know, it depends on your choice. So we have both types of signals, and so what is the truth? Are we predominantly seeing this signal in emission or in absorption? This is for the next slide. So in any case, both if I see the signal in emission and absorption, or the intensity of the radiation that I can measure, depend on this ratio, T gamma over Ts. T gamma we know precisely, so the only step that we need to do in order to be able to make our own prediction is just to compute Ts, so the spin temperature. How do we compute the spin temperature? So what determines the spin temperature is very interesting physics. So there are an atom sitting in nowhere in the universe has possibilities to interact at least with three types of interactions. First of all, it interacts with the CMB photons. So the CMB photons, when they interact with this atom, what they're trying to do is just to drive the spin temperature to the CMB temperature. That is, they are trying to adjust the level of atoms that are sitting in the excited state with respect to the ground state in a way that is consistent with the temperature of the CMB. So in that case, Ts would go to T gamma. The alternative process by which H1 atoms interact with the rest of the universe is through particle collisions and scattering with UV photons. That is, particles could be other hydrogen atoms or free electrons, molecules, anything you have there. These try to shake up this statistical equilibrium between the two levels, and so by doing so, they drive Ts away from the T gamma, from the temperature of the CMB. The same is true for absorption or scattering of UV photons, for example, Lyman alpha photons or other continuum photons. They also drive Ts away from T gamma. So in order to be able to determine what is the actual population of the levels and therefore determine the spin temperature, you need to solve what is called the detailed balance equation, which is nothing else than the balance between processes that are bringing your electron population from the ground to the upper level and vice versa. So these are photons that are exciting, the processes that are exciting the atom, and these are processes that are de-exciting the atom. So you have collisions, as I said, UV photons and CMB stimulated emission and spontaneous emission. So these are all things that are bringing electrons from level 1 to level 0 and the opposite from 0 to 1. Okay? So there are essentially these three processes that we need to consider in order to determine if Ts, the spin temperature, is higher or lower than the CMB. So let's start to consider first collisions. Okay, suppose you have only collision, forget all the other terms. Then well, before I do that, sorry. So again, what you can do is just because we have these three processes, the CMB, the essentially collisions with atoms and photons, we can rewrite again the radiative transfer equation for the spin temperature in the Rayleigh-Jeans regime. And so the spin temperature is a very simple expression that depends on these three interactions that I just discussed. So this is for the CMB, collisions with atoms, scattering with UV photons. And so we can define also, we have defined the temperatures of the kinetic temperature and the color temperature of the radiation field. So these are all the coefficients that enters here. So the kinetic temperature is defined in the usual way as the ratio of the collision coefficient. The color temperature is the ratio of the scattering events that go from ground to up and up to down. And so in most cases, though, we can say that Tc is essentially equal to the kinetic temperature. So the color temperature of the radiation, because the UV photons interact also with atoms and there are recoils, Doppler effects, so the two temperatures become the same. So this can be shown easily. So this is the expression for the Ts. This is an equation that tells us what is Ts as a function of this collisional coupling coefficient. So this is collisional and this is UV scattering. Okay? Nice. So as I said, suppose that we only have collisional coupling. So there are only the population of the levels can only be changed by collisions with atoms. Let's forget about UV photons for a second. Then what happens? Then if you only have collisional coupling, then you can, which has this formal expression, this is the absorption coefficient, this spontaneous emission, energy gap between the two levels, C and V temperature. Now, if you only have that coupling, so no UV coupling, no coupling with the photons, then you find that the critical overdensity at which this collisional coupling constant for HH collision is equal to 1, is given by this expression. Okay? So this is that means that collisions are important only in overdensities that are larger than this value, larger than essentially 1. Okay? But as you come down to lower redshift, SC becomes extremely small, and therefore the collisional cannot change the population level distribution that the CMB is trying to set. Remember that the CMB tries to bring the spin temperature to its own temperature, to the temperature of the CMB, while collision tends to drive away. Collision, this equation shows, are not able to do so as you come down below redshift 70. Why is that? Because the universe is expanding, density is decreasing, and collisions between collisions become less and less common. And so, if this is true, remember that if Ts is equal to T gamma, then the temperature of the cloud will be the same as the CMB, so the radiation will become invisible. This is bad news. Fortunately, though, these UV photons are helping us a lot. And this is a very important effect that couples the UV radiation with the hydrogen, neutral hydrogen atom, and it's called the photoism field effect. It was actually proposed by these two scientists. So how does it work? You work in, remember that what we want to do is just to drive the ratio of the atoms that are sitting in this level with respect to that one away from the ratio that the CMB would like to set. And so we have to scramble up these numbers. And so Lyman alpha photon scattering is exactly what is doing this for us. So it happens that when an atom sitting here scatters a Lyman alpha photon, is initially excited, is a resonance scattering, so it's excited to some higher level, in the 2p level, and then decays in the other ground state level, or vice versa. So this coupling with UV photons can scramble the level population, and the level at which this can be achieved is expressed by the X alpha coefficient that appeared in our formula before, with P alpha being the integrated scattering rate over the line profile. Okay, so these photons, the UV photon scattering increases the coupling coefficient and drives the spin temperature away from the CMB. This is very good. At this point, we are ready. We have everything. So if we have we have an expression for computing the brightness temperature. We have our small radiative transfer equation. And so what we would like to do is just now to compute the power spectrum of this 21 centimeter radiation that we are going to detect. So to do so, we proceed in a standard way. So we define the fractional perturbation of the brightness temperature. so which is defined by TB minus the mean of the brightness temperature divided the mean, so it's a zero mean field. So we do the Fourier transform, and then we do the average ensemble of modes and define the power spectrum exactly as we do in cosmology constantly. And so we also have the dimensional version. So in this case, we have the delta square, which is our dimensionless power spectrum. Good. So we are ready to compute that. So let's see now what, if we do the proper calculation, we put all these ingredients into the cosmic evolution, what do we get? Well, the first graph shows how the temperature of various temperature that are involved into the computation of the 21 centimeter power spectrum are evolving as a function of redshift. So first of all, we have to the dashed line of the top is the evolution of the temperature of the C and B, the 1 plus Z that we know and love. Okay. Now, the dotted lines is the evolution of the temperature of the gas. Okay, and remember that the gas after decoupling evolves adiabatically, so the temperature drops of 1 plus Z squared, not linearly, as the C and B. And so coherently, the gas temperature, the kinetic temperature of the gas decreases, stays below, so the gas is colder than the C and B. Now, the solid line is the temperature that we are after. There is the spin temperature. So at high redshift, so redshift, we're talking about redshift 300, for example. At 300, you see that the three temperatures are all equal, and after that, the spin temperature follows the kinetic temperature of the gas. Why is that? Because the density is high enough that the collisional interactions keep the spin temperature tied to the kinetic temperature of the gas. But as we have seen, about redshift 70 or so, the density has decreased so much that collisions are not efficient anymore. And in the absence of anything else, the spin temperature goes back to the to the C and B temperature. See that spin temperature moves from the decay, from the kinetic temperature, back to the C and B. So the C and B is taking control. This is the absence of any radiation from any UV radiation. So it's like in the universe there are no UV photons. And correspondingly, you can also compute from our formula, you can compute also the differential brightness temperature against the C and B. So as you see, temperatures are all negative because the spin temperature is always below the C and B. So this signal would, if in this simple universe in which nothing happens other than the expansion, we will see the 21 centimeter in absorption. And the intensity, you see, it's, the amplitude is pretty large, minus 40 millikelvin. The question is that this point here, this is a clear signature of any cosmological standard cosmology model with expansion, right? Because this is, there are no stars, there's no astrophysics here, just an expanding universe. In the dark ages, this probably is a very good approximation. So this thing, we can believe to this graph up to the time at which the first stars form. Then UV photons are produced and things will change, as we'll see in a second. But up to redshift 40, above redshift 40, this representation should be pretty accurate. And in fact, we would predict that this minimum, this strong signal should be present, must be present, I should say, around redshift 90 to 100. Okay? So if we were able to measure this signal, 21 centimeter at redshift 90 or 100, then we would see this signal, which is a perfect way, by the way, to have an independent test of cosmological parameter, because remember that the amplitude of this minimum, as I showed before, depends on the cosmological parameters. Okay? Where is it? Yes, this one. You see that we have things like the Hubble constant and also the shear of velocity, which is also measured, can be derived from peculiar velocities of the gas at this very high range. So that would be very good. What is this is an important result. The thing is that experimentally this is very hard. Why? Because the redshift 100, we would receive this radiation at the frequency which is 1420 megahertz divided by 100. So that is 14 megahertz. 14 megahertz, our atmosphere is totally opaque. But, for example, if we go from space or maybe on the moon, where the atmosphere is not interfering, this type of experiment could be done and will be done. There are people that are thinking about doing that. But so this is for the very high range stuff. But all the reionization is not included yet. So all the action that is produced by the first stars and by their radiation and their interaction with the gas is not yet included. So we need to do that. And so this is the same now, but in which we have included the fact that the gas is, that stars are forming, they produce UV radiation, which therefore provide an extra coupling between the spin temperature and the kinetic temperature. And at the same time, the stars also ionize the gas, which is not good for the 21 centimeter because they would, reionization of course destroys H1, which is the emitter that we are looking after, from which this light comes. But this is what it is, and so again, this is the same plot. Now T gamma is dotted line, Tk is the solid line, and the spin temperature is the thick line. There are two different reionization models here. So you see that up to 100 or something, the evolution comes down. The temperature of the gas decreases, but then it increases again due to the fact that now we have included reionization, and as we have seen from the simulation, the temperature tends to go to very large values, 10 to the 4 or so. This is the mass average temperature, so that's why it only gets to 10 to the 3, because there is still parts that are cold, but the gas in the bubbles are instead hot. So this is these are two, this is just an example with some evolution of the ionized fraction as a function of redshift, which may not be necessarily representative, but just an illustration. And now, instead of having the signal here in the brightness temperature, we also have a peak of emission, which should take care around redshift 12 and continue down until the reionization is totally destroy the neutral hydrogen. So this is the signal we are after. So this is comes from redshift that are from 13 to 6 or 7 maybe, depending on the reionization history. And this is what we hope to measure. Now, a global view of this brightness temperature evolution is exemplified by this picture, which summarizes essentially everything I've said in this second part of my lecture. So suppose that this is a simulation of the 21 centimeter brightness temperature evolution. So the size of this cube, it's 1 gigaparsec on this light cone with a size of 1 gigaparsec, and you go back in redshift down to this is redshift 100. Okay, so and we are evolving down to redshift 6. So let me explain what's happening in the light of what we've learned so far. So in the dark ages, where the gas is still cold, colder than the CMB, and there is a little bit of coupling between the spin temperature and the kinetic temperature due to collisions. As long as collision can manage to keep it, we do see absorption. Okay, because the gas is colder, and we have signal, because the temperature of the spin temperature is not the temperature of the CMP, but the temperature of the gas, and therefore we do see it in absorption. This is a signal from the dark ages. But then the signal disappears, and in fact it goes to 0 here for some time, until the stars appear, and by producing the UV radiation that provides an efficient Lyman alpha coupling via the photoresistant field effect, then the signal, the spin temperature gets coupled again to the kinetic temperature, and we have a strong absorption signal. But we may also add another ingredient that is becoming more and more studied recently, the fact that the stars associated to the first stars, it may also have a population of X-ray binaries that are well known to exist in all galaxies that we see around us. So if there is also this a little bit of X-ray heating, then could be very important because it produces a preheating of the neutral region. So X-rays are able to heat the gas without fully ionizing, so keeping the ionization level very low, but at the same time heating the gas. And so heating the gas changes the kinetic temperature, and so you see these features also in the 21 centimeter line. So this is the cosmic dawn, where the first stars are formed, and you still see a signal from there between redshift 15 and 27. This is becoming increasingly difficult for experiments, of course, because they are still working at low frequencies. So maybe we get there, maybe not. But then when in the EOR, in the epoch of reionization, what happens is that the IgM, the intergalactic medium, becomes warmer than the CFB, and so we start to see the signal in emission, and at the same time the spin temperature is coupled by all this UV radiation to the kinetic temperature, and therefore we do expect to see this gas very well in the reionization. Now, the advantage of the 21 centimeters is that if you tune the frequency of your receiver, you can study any redshift that you like. So if you want to study 8.27, you tune your receiver at 8.27, corresponding to the frequency corresponding to 8.27, and you have a map like this one in the sky of the entire structure of the ionized and neutral regions. Okay, so you do see an image of the structure of reionization, essentially. Of course, this is the final goal. Before we get to there, and we need to do exactly as we do for the CMB. We have to deal with all the foregrounds, but as with the CMB, we have been able to do that. So we hope that we will also be able to remove these foregrounds produced by astrophysical and terrestrial contaminations, including cellular phones, I have to say. And be able to dig out the signal. So if this is possible, we will get these beautiful maps. These are the final goal. We also have, as an intermediate step, the possibility to determine the power spectrum that I was mentioning before. So this is a simulation you will see here, basically the brightness temperature map. This is 750 megaparsec on the size. And so the blue is when the signal is in emission, so the temperature, the spin temperature is higher than the CMB. Red when it's below that, so red is absorption. And on the left panel you will see the evolution of the power spectrum of the CMB as a function of the wave number in inverse megaparsec co-moving. So if I run now, you will see redshift here, so we start from redshift 119, where everything is neutral, and the delta PB is minus 14, as we have seen before. And then we can see the movie. So you see the power spectrum is should increase. No, sorry, I'll run it again. It's a little bit, don't worry, I'll do it again in a second. Please, it's not working properly. If you will. Okay, let's read it again. Okay, now, so you see that the power spectrum is increasing as more and more power is produced by the structure formation that is increasing the overdensity, and this is the boost when essentially the cosmic dawn, where the first stars appear and couple the UV, you see there are several features that are interesting until the gas is totally burned out, the neutral gas is totally burned out, and the signal disappears. So there is a very interesting evolution of the power spectrum as a function of redshift that depends on the type of the bubbles and sizes of the bubbles that you get that you can see here in the brightness temperature map. Okay, so at some point, depending on the structure of the image is mapped into the power spectrum. So this is what we want to, we hope to observe with particularly SKA, but there are other experiments that are going on. And so this is the way in which we think we can study ionization today. And I'll stop here, and if you have any questions, I'm here.